Good morning, everyone. New week again. Okay. Last week we learned about simple harmonic motion and waves, traveling waves. You can see actually what we learned so far is step by step. And firstly, we learn simple harmonic motion, and it is the oscillates like in a specific form, like a sinusoidal form. And after that, we learn about the traveling wave. You can see the traveling wave. We also can be represent the traveling wave in a sinusoidal motion for some wave. Yeah, because you can see like some wave it can be it will move in a sinusoidal form. So you can see step by step we learn the simple harmonic motion. Actually, it's ready for what we will learn the like traveling wave. And today, in this week, we will learn um, the some like a new term called superposition and standing waves. Actually, these two terms also relate to waves, just some like typical phenomenon like for us. And after I talk about that, you will learn. You will know what is superposition, what is standing wave. Yeah, and after we learn the wave last week, and we will learn. Actually, we will explore more about the waves. Okay. Let's start today's class, and let me share my screen. Okay. Uh, let's see. Yeah. Mm, sorry, I think I didn't share web. Okay. Yeah. Oh, no. Okay. Okay. Let's start today's class. Today we will talk about superposition and standing wave. Waves. Actually, those kind of phenomena is very typical for waves. And today we will learn what is superposition, what is standing waves, and how can we explain the theory thing behind that. Okay, let's continue. And for the superposition, chapter 16, we will learn in this week, and it's talk about the superposition and standing waves. And this chapter's goal is to use the idea of superposition to understand the phenomena of interference in standing waves. Yeah, we will try to understand what is interference and standing waves? How can they come out? Yeah, and okay, let's try to preview looking ahead at some term. Firstly, we will learn like the superposition. I don't know if you guys noticed that when the two water wave here, when the two water wave meet, there is this is the source, this is the source. Actually, there is another one, but it's we can ignore that one. When the two water waves meet, the motion of the water is the sum, or we call it superposition of the waves. Yeah, if there is a source, there is a other source, and then the wave will travel, and this wave will travel, and here uh, in this area, the wave will be the sum of the waves, the sum of two waves. We call this phenomenal superposition. Like uh, in one position, there are two waves. It's such as plus position like that. Yeah, and you will learn how this interferes can be constructive or destructive, leading to larger or smaller amplitudes. Yeah, uh, you can see like when those two, yeah, when those when those two like waves travel to the far place and they meet in the middle position, in the middle area, sometimes they will like the wave will the amplitude of waves will be larger. Sometimes it will be smaller. Yeah, we call it constructive if it is larger. Otherwise, the smaller we call it destructive. Yeah, we will learn like when the constructive will happen and when the destructive will happen. Yeah, this is what we will learn. Okay. And also we will like learn standing waves. The superposition of waves on a string. Yeah, you can see like there are two waves. There are two different waves. And the superposition of waves on a string can lead to a wave that oscillates in place. A standing wave, you can see here, those two waves on a string, like can lead a standing wave. You can see here, it is standing there, like stop there, like that. Yeah, so we will learn how this standing wave happen and why this standing wave happen. Yeah, yeah, we will learn like the patterns of standing waves on strings and standing sound waves in tabs. Yeah, okay, let's continue. And also we will learn like yeah, let's try to like looking back something. Last week we learned like traveling wave. Yeah, in chapter 50, you learned the properties of traveling waves and relationships among the variables that describe them. Do you remember that? Like, yeah, I think here. Sorry, let me try to. Uh, oh, yeah, here. You can see here, this is the equation we learned in last week, and the V equal lambda multiple F. This is a wavelength, this is a frequency. Yeah, and also like this, like then you can like use velocity and the wave lambda to like calculate the frequency. Yeah, you according this equation, and you can see for a string, like the velocity, we can also like we have the other equations to calculate it. Like yeah, I don't know if you remember that. It is but depend on the string tension. Am I right? And the identity, the linear identity. Actually, the linear identity can be represented like divide L. Yeah, do you remember that? And also, this is for the string wave, and for the like sound wave, it is just equal. It is related to the temperature and the molecular like a quantity, a molecular mass. Do you remember that? Yeah. Actually, you can see the property of traveling waves and the relationships among the variables that describe them. Yeah, this is what we learned in last week. In this chapter, you will extend the analysis to understand the interference of waves and the properties of standing waves. Yeah, based on this one, we can extend the analysis to understand the interference of waves and the properties of standing waves. And let's learn how, like what. Okay. Before we start this class, let's try to like stop to think one question. One like a 170 hertz sound wave in air has a wavelength of 2.0 meter. The frequency is now double to 340 hertz. What is the new wavelength? Actually, this one is quite easy. Am I right? We just write the equation for this one, like V equal what? Do you remember that? Yeah, we just write like yeah, try to don't look back the slides. Try to remember that. Yeah, V equal what? Lambda multiple F. Am I right? Yeah, here 170 hertz sound wave in air has a wavelength of 2.0 m, which means you know the frequency, you know the lambda. What you will learn? You will know the velocity. Does it make sense to you? Yeah, velocity equal what? Yeah, like two two multiple one. Am I right? It is. And then the frequency is now double to 340. What is new wavelength? Which means new wavelength equal what? Velocity divide frequency. Now the velocity is the same thing for the sound wave. Am I right? Yeah, so which means we will learn we know the velocity is 340 and frequency is what? Change to 340. So the wavelength is what? Yeah, it is obvious. It is one. Does it make sense to you? Yeah. Okay. Let's continue. Yeah, you can see the answer is one. Yeah. So just try to remember these equations, and you will learn how to calculate the frequency, the period, the velocity, yeah, and the wavelength. Yeah, this is just the traveling waves. For the traveling, what we need to calculate? What do we need to calculate? Yeah, and this is today's goal. And firstly, let's try to understand the principle of superposition. And then we will learn about standing waves. What is standing waves? How these standing waves come out, and like how to represent these standing waves. Yeah. And after that, we will explore standing waves on a string. And finally, we will study standing sound waves. Yeah, you can see here. Actually, you can see this part is the standing waves on a string. This is the standing sound waves. Yeah, it's different standing waves. One is string, the other is sound waves. Yeah. Okay. Let's continue. Okay. Firstly, let's talk about the principle of superposition. There is a very obvious example. Yeah, there is PC machines. I think some students may use this one. Actually, I also didn't use this one before, but I watched this in TV or some video. Yeah, you can see the pitching machine will uh, uh, pitch some balls if those machine send out the ball at the same time, there are two baseball here are throw across the same, and at the same time you can see actually they will meet in this point. Am I right? If they meet, if they crash in this point, if they hit with each other in this course, they will they will be deflected, and this ball, A ball, will be hit to this direction, and B ball will be hit to this direction. You can see at the same time they cannot be in the same position. Yeah, for a real thing, for a real ball. Am I right? Does it make sense to you? Yeah, you can see they hit with each other and then deflected. Yeah, they cannot be what two two balls cannot be in one same position. Does it make sense to you? Yeah, but for waves, it's not like that. You can see there is a like a sound wave. There is a loud speaker. Yeah, this is waves. Like a wave, and also there is wave. And those two waves, they can pass through one another. Actually, they are not like balls. Yeah, the balls they have the real body, so they cannot pass through like with each other. They cannot pass through one another. So, but for the waves, they can pass through one another. Both observers, you can see Alan and Bill, would hear undistorted sound, despite the sound waves crossing. Yeah, you can see the sound wave can cross it. Like the waves can be the same like position here. Does it make sense to you? When two waves are present simultaneously, the displacement is the sum of displacements of two individual waves. For example, here is wave A, here is wave B. In this position, like the displacement is the sum of the displacement of wave A and wave B. Does it make sense to you? Yeah, because they just have the like a displacement sum like a phenomenon, like a situation. Yeah. So we call this phenomenon like a superposition, like when two, you can see here, when two or more waves, yeah, not only two, like you can 3, 4, like unlimited waves are simultaneously present at one single point in space. The displacement of the medium at that point is the sum of the displacements due to each individual wave. We call this situation superposition. Does it make sense to you? Yeah, because you can see for the waves, like two waves can be exist in one position, not like the real thing, like the real ball we talked about just now. The waves can happen in the same like can be exist in a same like position. This is we call it superposition. Does it make sense to you? Okay. After we talk about the principle of superposition, let's try to understand this one. Yeah, you can see to use the principle of superposition, you must know the displacement that each wave would cause if it were alone in the medium. Like here, you can see there are two waves. One is like a triangle, the other is square, and they just this wave travels to this direction, this wave travel to this direction, and like if they overlap, which means they will be in the same position. Yeah, here is like the position, and then the superposition situation will happen. Like the displacement will be added. Does it make sense to you? Okay, then yeah, you can see it just crosses. Then you must go through the median point by point and add the displacements due to each wave at each point. You can see at this time t0 and they didn't meet with each other, and t equal 1, they almost there, they almost meet but haven't. Yeah, and let's continue. Oh, sorry. And then they okay, like the two position of two waves is called interference. You can see here those two waves they meet with each other in this position, and we call it superposition. Superposition of two waves is called interference. Yeah. And you can see those two waves, the displacement, they added with each other. We call it constructive interference. Yeah. Usually, constructive interference occurs when both waves are positive and the total, yeah, both waves are positive, and the total displacement, yeah, total of the media is larger than it would be for either wave separately. Yeah, you can see those two. This is one A, this is B, and they will add with each other, and then the total like displacement medium is larger than it would be for either wave separately. Yeah, and then it will continue, and this is what they will like left, and then it will like travel to separate direction. Yeah. So this we call it a constructive interference. Yeah, because both waves are positive. Does it make sense to you? Okay, let's continue. Oh, sorry. And destructive inference is when the displacement of medium where the two waves overlap is less than it would be due to either of the waves separately. You can see this is one, sorry. Yeah, this is one wave. This is the other. You can see their displacement is opposite. One is positive, the other is negative, which means when they match with each other, they will like minus with each other. They will not, they add with each other, but one is positive, the other is negative, which means the total is less than separately. Does it make sense to you? Okay. Yeah, you can see like the destructive interference, the uh, as two waves like goes to its direction, and then they meet, and then they will like kind of they sound, but one is positive and the other is negative, so they will like become less, like the displacement is become smaller, and then you can see if those two, yeah, because those two waves are same, only one is positive and the other is negative. So in this place, in this term, and they just like the net displacement of the medium is zero, and then continue, and yeah, they will like separate finally. Yeah. Okay. Does it make sense to you? This kind of like interference, we call it destructive interference. Try just like try to you need to know like during destructive interference, the energy of the wave is in the form of kinetic energy of the medium. You can see like when the wave moves, yeah, the energy will now disappear. Am I right? So the like energy is in the form of kinetic energy of the medium, which means which this energy makes the medium move. Kinetic energy, which means like they have to move like energy. Does it make sense to you? Yeah, just remember this one. Okay, let's continue. Oh, let's review some like quick check questions. The first one is like a two-wave pulse on a string approach each other at speeds of 1 meter per second. How does the string look at when t equal 3 seconds? Here, for the question, t equals 0. So because the speed is 1 meter per second, 1 meter per second, which means when t equal 1, and then this one remove 1 meter, am I right? Like this, sorry. And this 1 meter, does it make sense to you? This is t equal 1. And t equal 2, and continue. This is t equal 2, and this is t equal 2. Yeah, does it make sense to you? And t equals 3. Wait, maybe, sorry, let me try. Okay, t equal 2. Let me use blue. Okay, here, t equal 4. Let me use green. You can see it will continue like this. Am I right? So this one, it's just like this. And then it like because it will sum together. Am I right? So which means the final, let me try. Yeah, The final will just like this. Does it make sense to you? So what's the answer? I think it's obvious, am I right? It is C. Does it make sense to you? Yeah, they will add together. Yeah, it is C. Does it make sense to you? Okay, let's check the other one. Two wave paths on a string approach each other at speeds of 1 meter per second. How does the string look at equal 3 seconds? Yeah, it's a same question, but the wave is different. Yeah, you can see in that question, this wave is positive, but in this question, this wave is negative. So let's check how does the string look at time equal 3 seconds. Let's say we use when t equals 0. Yeah, this is just like this one. Yeah. Oh, what's this? Okay, sorry. And this is t equals 0. And then t equal 1, which means this will just like this. And this will move like this. And when t equal 2, it will like this. And this will like this is t equal 2. And t equals 3, which means this is t equals 3, and this is t equals 3. Yeah, they will like they will meet in t equals 3. And then you can see this is negative, this is positive, which means it will be minus with each other. And then this will left because yeah, this will left this part. Let me try to give a more. This will left this part. Yeah, because this part will remove and this part. So what's the answer? It's obvious, am I right? It's B. Does it make sense to you? Yeah. Okay, yeah. If you met this kind of question, that you to find the like two waves, the constructive or this disconstructive, and you just like move one time by one time and to see how the final like wave look like. Okay, let's check the other one. Two waves on a string are moving toward each other. A picture at t equals 0 seconds appear as follow. Yeah, this is t equal like 0 seconds. It's an initial time. And how does the spring appear at t equal 2 seconds? Actually, it's a similar thing. You can see here is just like t equals 0, and you need to find t equal 1. Let's try to yeah, t equal 1, which means it will move like this. And t equal 1, it will move here and here, and here. Does it make sense to you? Yeah, just move. And t equal 2, which means continue. This one and sorry. And uh, this one and this one and this one. Yeah, so yeah, you just need to like add those two together, and you can see, and because this part will be removed, does it make sense to you? This part will be removed because it will, and then this part will be left, and this part, yeah, it just divide, and it's just like this. So which one? I think it's obvious. It's AM, right? Yeah, just get the left thing. Yeah. Okay, let's try to, yeah, we have already talked about the what is superposition. What is superposition? You can see like two waves or two or like more waves, they met in a same position. Yeah, there will like have the superposition phenomenon. Yeah, and for the superposition, there are like two different superposition situation. One is constructive, the other is disconstructive. Does it make sense to you? Yeah, because sometimes the wave is the positive, sometimes it is the negative. Yeah, and they just they need to add with each other. Like sometimes the total will be sum and it will be larger, and sometimes the total will be smaller. Yeah, does it make sense to you? Okay, this is for the super waves that are trapped and do not look like the travel in either direction are called standing waves. Actually, we have already talked about the traveling waves. The traveling wave means there is a source and the wave will travel through the medium, yeah, to different direction. The standing wave, which means these waves trapped and they do not like the travel in either direction. They seem still there. So we call this is standing waves, which means it stands there. The waves do not move. Yeah, like individual points on a string oscillate up and down, but the wave itself does not travel. Yeah, actually, I can know it is still it moves, but it just moves. Like it just oscillate up and down. But it will not travel. That makes sense to you. So for the standing waves, the points on this wave, like it just oscillate up and down, but it will not travel. And this wave, we call it a standing wave because the crest and the stones stand in place as it oscillates. Yeah, just up, down, up, down, up, down. Here is still up, down, up, down, up, down, up, down. Yeah, so we call this kind of waves standing waves. And we will talk about how these standing waves generate and why it's just like that, and we will talk about the theory behind this one. Yeah, actually, the superposition. Firstly, the superposition can create a standing wave. You can see as two sinusoidal waves of equal wavelength and amplitude travel in. Let me see if I to. Yeah, I have already shared my screen. Sorry, I just want to double check. As two sinusoidal waves of equal wavelengths, you can see those there are two sinusoidal waves and they have equal wavelengths and amplitude. Yeah, the wavelength is equal and the amplitude is equal. You can see here lambda. The amplitude A here is also A and in opposite direction. Yeah, one is to the left, the other to the right. And along a string, superposition will occur when the waves interact here. A superposition will occur here when the waves interact. Actually, this superposition can create a standing wave. Yeah, we will see how to this create a standing wave. Yeah, this will show how to create a superposition, create a standing wave. Okay, let's talk about how a superposition creates a standing wave. There are two different waves. You can see here the red one represents the wave moving to the right, and the orange one represents the wave moving to left. And here you can see here there is a point. This one in this point it should the red one plus the orange one, but it is the blue one. It is the blue one and the red one equal the same point, which means the yellow one here is 0. That makes sense to you. So here it should be the zero displacement. Yeah. So this means it's a little sorry. Yeah, there is a little difference. It is here. Here should be the. What's this? Yeah, here should the this place, and yeah, you can see every point is just the every point in the blue wave. This blue wave is the superposition wave from like the yellow one and the red one. The points, every point in the blue one is the red one plus the orange one. Yeah, does it make sense to you? So like in this point, and the superposition wave is just like this, and in this like a time, and it's just like this, a similar thing. And in this time, and the crest of the red and the orange of the sun, yeah, meets. So the wave cancelled. It's just a one line, and then sorry. And here the same thing, and here it's just like I think it's just the here. This is just the displacement equals zero, and then here, yeah, this is the blue one. How the blue one came out like a like a generated, and those superposition creates a standing wave. This blue, this like a blue line, this blue wave is a standing wave. You can see if you like this is like analyze how this superposition creates a standing wave. The two waves are represented by red and by orange in the previous figures. At each point, the net displacement of the medium is found by adding the red displacement and the orange displacement. The blue wave is a resulting wave due to superposition. The blue wave is the wave you would actually observe in the medium. Let's try to choose the right one. Okay, you can see this is this blue waves. Yeah, it's just like the superposition wave, the standing wave, like that orange and blue and like the red wave generated. Yeah, in the standing wave pattern, there are some points that never move. Yeah, for here, because these points is always like those points, we call it nodes, and are spaced like lambda divided to half lambda apart. Yeah, because here, from here to here, it is lambda, and those half lambda is those points never move. You can see here. Let's talk about here. You can see here there is lambda, so which means there are some like points, for example, here, yeah, here, they will never move. Yeah, we call it nodes. Those points like never move and are spaced half lambda apart. And also there is another node, we call it antinodes, are halfway between the nodes here. And where the particles in the medium oscillate with maximum displacement, yeah, you can see, you can everywhere see. Yeah, here is the antinodes. And the wavelength of a standing wave is twice the distance between successive nodes or antinodes. Yeah, it obvious. This is wavelength, and the nodes is yeah, it's half lambda, and the antinodes also like it is half lambda. So does it make sense to you? At the nodes, the displacement of the two waves cancel one another by destructive interference. The particles in the medium at the node has no motion. And you can see here, the particles in the medium at the node has no motion. Yeah, because the distance it cancelled one another by destructive interference. And at the antinode, the two waves have equal magnitude and the same sign. So constructive interference at these points give a displacement twice that of individual waves. Does it make sense to you? Yeah, because like the original individual waves is like A, so which means this antinode is 2A. Does it make sense to you? The intensity is maximum at points of constructive interference and zero at points of destructive interference. Yeah, does it make sense to you? You can see here the intensity is maximum at points of constructive interference and zero here is maximum, and the zero at the destructive interference. Yeah, this is what we should know about the what is nodes. Yeah, there are some those are the some definition. What is nodes? What is antinodes? For the nodes, what's the characters? What's the features? For the antinodes, what is the character? What's the features? Yeah, let's see some quick questions about the antinodes and the nodes. Yeah, what is the wavelength of this standing wave? You can see here, this is a standing wave, am I right? So we have already talked about this, the there is antinode, there is nodes, there are antinodes. The nodes should be in the half lambda. Does it make sense to you? So there should be two node, there will be 1 lambda. Yeah, so which means, for example, here is the start. Here should be the lambda. That makes sense. If here is the start, here should be the lambda. So what's the wavelength? It should be 1. Does it make sense to you? According to the definition we have already talked about. Okay, so it is C, 1 meter. Okay, any question, just let me know. Okay, let's talk about the standing waves on a string. There are some there is a term, we call it reflections. What does that mean? Like a wave pulse traveling along a string attached to a wall will be reflected when it reaches the wall or the boundary. For example, here is a boundary or a wall, and you just give a wave this string, and there is a wave travel to this direction, and then this wave will be when the wave meet this boundary, it will be reflected. Does it make sense to you? I think if you this is a very common phenomenon. Yeah, and all the wave, if this situation happen, all the waves energy is reflected. Hence, the amplitude of a wave reflected from a boundary is unchanged. You can see there is an amplitude. After he reflected, the boundary is on the amplitude is unchanged. Only it is inverted, here is positive, here is negative. Yeah, the amplitude does not change, but the pulse is inverted. Does it make sense to you? If you do the lab, and you will see it is just when this wave meets the boundary, it's just reflected, and then it will goes to this wave. Yeah. Okay, let's continue talk reflection. We call this situation reflection, and the wave also reflect from a discontinuity. a point where there is a change in the properties of the medium. Like here, discontinuity, where the wave speed increases. You can see there are two different waves. If this wave, this wave meet another different medium, it will also have the reflection situation. Yeah, and at a discontinuity, some of the wave's energy is transmitted forward and some is reflected. You can see here is a stream, here is a different stream, and when the wave meet here, it will reflect some and it will transmit some. Does it make sense to you? Yeah. This is also one kind of reflection situation. Yeah, we call this like situation like a discontinuity. Yeah, because it's not the same thing. It's just like a discontinuity. Yeah, does it make sense to you? Okay, like when the string on the right is more massive here, like the here in the right is more massive, it acts like a boundary, which means this seems like a boundary. So the reflected path is inverted. Yeah, also it will like transmit some and reflect some. But if this string on the right is more massive, it will just like a boundary. So it will reflected. The reflected path is inverted. But you can see here, this one. Since this one, the massive is smaller than the left part, so the inverted wave is just like there is no like a reflect. There is no like this. The reflected pulse is now like reverted. Yeah, doesn't make sense to you because it just you it's discontinuity, but it's not like a met a word or a boundary. Yeah, does it make sense to you? Okay. Yeah, try it yourself through the glass darkly. Yeah, a piece of window glass, you can see, is a discontinuity to a light wave. So it both transmits and reflects light. To verify this, look at the windows in a brightly lit room at night. The small percentage of the intro light that reflects from window is more intense than the light coming in from outside. So reflection dominates the windows, show a mirror-like reflection of room. Now turn out the lights with no more reflected intro light. You will be able to see the transmitted light from outside. I think this situation, this phenomenon, you usually see it when you like open the light in a room, and you will see like a mirror-like reflection of the room. But if you turn out the light, and you can see the light from the outside, yeah, this kind of like a wave continuity situation. Yeah. Okay, let's continue. Let's continue to talk about creating a standing wave. You can see we talk about the superposition, like creates a standing wave. Also, standing wave can be created by a string with two boundary where reflections occur. Yeah, it's just like a two like a same like wave. Yeah, you can see if you wiggle the string here in the middle, and there will be one wave travel to this direction, one travel to this direction, because there is a boundary, there is a wave, there is a wall, so it will reflect, and then it will, because it's the same like amplitude and the same like frequency and the same like wavelength. So when it meet in the middle, it's just like it will like create the superposition and like create a standing wave. Am I right? Yeah, it's a similar thing with the one before, or like we talk about, like a standing wave can be created by a stream with two boundaries where reflections occur. This turbulence in the middle of the stream causes wave to travel outward in both directions, and the reflection at the ends of the string cause two waves of equal amplitude and the wavelength. Just remember, if you want to create a standing wave, you need to make sure the two waves should be equal amplitude and wavelength to travel in opposite direction along the string. Yeah. Okay, let's talk about continue to talk about creating standing waves. Two conditions must be met in order to create standing waves on a string. Yeah, actually I talked about this before. Yeah, in those 30 minutes like that. Yeah, because the string is fixed at the ends. The distance at x equals 0 and x equal L must be 0 at all time. The distance at here is x equal 0. Here is x equal L because the total length of the string is L. So there are two addition. One is addition is the displacements x at x equal 0 and x equal L must be 0 at all times. No matter what situation happens, if you want to create in a standing wave, here the displacement here and displacement here are always 0. Started another way, we require nodes at both ends of the string, which means here is always the nodes. Does it make sense to you? Here always the nodes. Yeah, we know that standing waves have a spacing of lambda divided 2 between nodes. This means that the nodes must be equally spaced. Yeah. Does it make sense to you? Yeah, standing waves have spacing of lambda divided 2 between nodes, which means this node must be equally spaced. Otherwise, this situation will not satisfied. Yeah, does it make sense to you? Yeah, because if here, yeah, because it should be 0, I'm right, this place should be 0, and there is 2 lambda divided 2, and this is the other one, this is the other one, and then reach to here, it should be 0, I'm right, also should be 0. So which means the nodes must be equally spaced, otherwise here will not be 0. Does it make sense to you? Yeah. So yeah, this finger, yeah, here, this finger shows the first 3 possible standing wave more modes of a string. The mode number m helps quantify the number of possible waves in a standing wave. A mode number m equal 1 indicates only one wave. M2 indicates 2 waves. Extra. Different modes have different wavelengths. For any mode m, the wavelength is given by the equation, this one. Yeah, you can see if there is only one wave, yeah, only one wave, which means the wavelength is equal to L. Any mode m, the wavelength is equal to L. And if m equal 2, which means there are 2. The next possible standing wave is addition, which means the lambda m equal L. Yeah, does it make sense to you? Yeah, because for example, this one is the L, which means this is equal L, am I right? So which means the lambda equal to L. It's a similar equation, am I right? So if the here is just the total, yeah, I need to talk about it more clearly. The total here, the total length is L. the string as L, there is one node. One node we know it is lambda divided 2. Am I right? So which means here lambda should equal 2L divided M. Here is just lambda, is L, and it's just a one lambda. So lambda equal L. Yeah, when M to it's a similar thing. Yeah, does it make sense to you? Okay. A standing wave can exist on a string only if its wavelength is one of the values given by this equation. Okay. Yeah, a standing wave can this equation. Yeah, a standing wave can exist on the string only if its wavelength is one of the value given by this equation. Otherwise, there will be no standing wave. Yeah, because we talk about like a standing wave have a space between. This means that nodes must be equally spaced in the whole like a string length. So which means a standing wave can exist on string only if the wavelength is one of the value given by this equation. Otherwise, there will be no standing wave. Does it make sense to you? Okay. The oscillation frequency corresponding to wavelength lambda m equal this one. Yeah, because here we know like the lambda equal lambda m equal 2L divided m. And we also know like V equal lambda m f, am I right? So which means Fm equal V divided lambda m. Yeah, we have already talked about this in last class, like the like traveling wave in a string. Yeah, and then we just replace lambda m with this 2L divided m for a standing wave. And then we got this equation. Multiple V divided 2L. M equal 1, 2, 3, 4. Those means how many nodes in this standing wave. Different modes have different wavelengths. The mode number M is equal to the number of antinodes of the standing wave. Yeah, here which means there is one antinodes, two nodes, which here M equal 2, which means 2 antinodes, three antinodes. Does it make sense to you? The standing wave modes are frequencies at which the wave wants to isolate. They can be called resonant modes or resonances. Yeah, like this is just the definition. The standing wave modes are frequencies at which the wave wants to oscillate. Yeah, and they call it resonant mode or resonances. Okay, for a standing wave. Okay, let's check review some quick check questions. What is the mode number of this standing wave? You can see we talk about the mode number m equal what? The number of antinodes of the standing wave. Am I right? So here, this question asks me what is the mode number, which means we just need to know how many antinodes. Am I right? So how many antinodes in this wave, standing wave? 1, 2, 3, 4, 5. Does it make sense to you? So it is 5. Does it make sense to you? Yeah, number of antinodes. Yeah. Okay. Let's talk about the fundamental and the hair harmonics. I don't know if you guys heard about the harmonics. Harmonics means like a change based on a same number, like a change in a specific piece. Yeah, we will talk about the fundamental and the harmonics here. Like the first mode of the standing wave mode has a frequency here. Here, the first mode of the standing wave. Yeah, we know that. And this frequency is a fundamental frequency of the string. You can see here. This is the FM. The first means M equal 1, am I right? So which means F1 equal V divided 2L. This is, we call it fundamental frequency. This frequency is a fundamental frequency. All other modes have frequencies that are multiple of this fundamental frequency. Yeah, because you can see here, other mode just like a multiple M here. Does it make sense to you? Okay. Like the frequency in terms of the fundamental frequency is the allowed standing wave frequencies are all integer multiples of the fundamental frequency. Yeah, because here is the fundamental frequency, and the allowed standing wave frequency, like just a multiple m just from 1 to like unlimited number, but it is integer, like a number integer. The sequence of possible frequency is called a set of harmonics. Yeah, what is harmonics? The sequence of possible frequency is called a set of harmonics. It's just like based on this frequency, multiple like different multiple 1, multiple 2, multiple 3, which means the frequency one the first is V divided 12, the other is L, and like 2, 3, like 2, like 4V12. Actually, it is 2VL. Yeah, just like this, a set of harmonics called a set of harmonics. The fundamental frequency F1 is also known as the first harmonic. Frequencies above the fundamental frequency are related to as higher harmonics. Yeah, like because the higher harmonics are always related to the fundamental frequency. It's just like the multiple like multiple times of fundamental frequency. Does this make sense to you? Yeah, this is some like a definition for the fundamental harmonics and the like higher harmonics. The fundamental harmonics is just the like the harmonic the frequency is like fundamental frequency. Higher harmonics is just like the related to the fundamental frequency. Like yeah, does it make sense to you? This is the definition. When we talk about the fundamental harmonic and higher harmonics, what is that? Yeah. Okay. Let's see one example. Like I identify harmonics on a string. There a 2.5 meter long string varies as a 100 hertz standing wave with nodes at 1 meter and 1.5 meter from one end of the string, and at no point in between these two. Which harmonic is this? What is the string's fundamental frequency, and what is the speed of the traveling on a string? Like from a scratch, we will determine the total number of nodes and the antnode. This will allow us to find the mode number and thus harmonics. Does it make sense to you? So for these questions, like we begin with a visual overview in the figure, in which we sketch this particular standing wave and know the known and unknown quantities. We set up, yeah, here is a x axis with one end of string at 0, and the other is 2.5 because you can see there is a 2.5 meter long in the and the end of the string are nodes. Yeah, we talk about this here. The end of the like is always here. Yeah, this means the node must be equally and yeah, x equals 0 and L must be 0 at all the time, and 0, which means it's nodes. Am I right? So which means here is always nodes and here is always nodes. And also the question tell us like at the 1 and 1.5 is nodes. Am I right? And 1 here is nodes, and here is also nodes. Since like the nodes should be equally here, should be equally spaced. Am I right? Does it make sense to you? Yeah, so which means here should be nodes. Here should be nodes. Yeah, this should be the shortest distance between two different nodes. Does it make sense to you? Yeah. So we know that standing wave nodes are equally spaced. So there must be other nodes on the string as shown in the top figure. The bottom figure is a sketch of the standing wave mode with this node structure. Does it make sense to you? Yes, this is the standing wave. We sketch it, and yeah, we count the number of antinodes and of the standing wave to deduce the mode rule. Yeah, you can see the mode number is just antinode number 1, 2, 3, 4, 5. 5, I'm right. So which means the mode number is 5. This is the fifth harmonics. The frequency of harmonics are given by this one. Am I right? Yeah. Let's talk about the fundamental frequency is F1 equal F5 divided. Here we know the F5. Yeah, the question give us like 100 hertz. Like yeah, this is which means like the frequency, like harmonic frequency is 100. Then we can based on this one to calculate the fundamental frequency is 20 hertz. The wavelength of fundamental mode is lambda 1 equal to 12, which means the like it is 5 meter. Yeah, and so we can find the wave speed using the fundamental relationship of sinusoidal waves. Yeah, like this equation we will talk about a lot. Yeah, V equal lambda 1 F1 equal to is 100 meter per second. Yeah, does it make sense to you? Okay, and then let's assess this example. We can calculate the spin of the wave using any possible mode, which give us a way to check our work. The distance between successive node is lambda divided 2. The figure shows that the nodes are spaced 0.05. So the wavelength of M equal 5 mode is 1. Yeah, because this is half, am I right? The frequency of this mode is 100. So we calculate V lambda, yeah, which means the velocity for this wave is 100 meter per second. This is the same speed we calculated earlier, which give us confidence in our results. Does it make sense to you? Okay, let's talk about stringed musical instruments. Like the fundamental frequency, yeah, we have talked about what is fundamental frequency can be written in terms of the tension in the string and the linear density. Actually, you can see here. We know like the fundamental frequency is this one, like F1 equal V divided 2L. And we know like the V can be represented by this thing for a string. Yeah, we have already talked about in last week. Yeah, you have, if you forgot that, you can review that part. So we can like have this equation for the for the string, and we can represent the fundamental frequency with the string length, the tension, and the linear identity. Density. Yeah, density. When you plug a ball or string of an instrument, initially you accept a wide range of frequencies. However, resonance says to it that the only frequencies to persist are those of the possible standing waves. Yeah, this is a situation like when you plug a ball or string of an instrument. Initially, you accept a wide range of frequencies. However, the resonance says to it that the only frequency to persist are those of possible standing waves. Only like that standing waves will be persist. On many instruments, the length and the tension of the strings are nearly the same. Like the strings have different frequencies because they differ in linear density. So for the linear density, what is right? What is that? Do you know that? Do you remember that? What is this? If you know that it related to what, like the mass and the L for the string, does it make sense to you? So it yeah, if you review the class we have already learned last week, you will know that. Okay, let's continue. Okay, let's talk about this question. Which of the following changes will increase the frequency of the lowest frequency like a sound wave on a stretched string? Choose all that apply. You can okay, let's write down the equation here. F yeah, the lowest frequency, which means the fundamental frequency. Like fundamental frequency is equal V divided 2L equal what? Equal 1 2L uh, square root tens divide linear intensity and equal the like this is M divided L, which means equal to L L. Doesn't make sense here, which means it is 1 2 T S M. I'm right. Let's check the first one. Replacing the string with a thinner string, which means like the mass will become larger. Does it make sense to you? So let's try to. Yeah, this which means the string will, which means this one should be like a increase, and then like the frequency you can see here it is in this here, which means the frequency will decrease. So this one is not right. Increase the tension in the string, which means increase this one. Then this frequency will increase. Am I right? So which this one is right. And plucking the string harder. I think this is not related to the frequency. Yeah, because the frequency is related to the string like property. Like double the length of the string here, which means this one will increase. Which one? This one will decrease. Yeah, it's not right. So the right answer is only B. Does it make sense to you? Yeah, here. Oh, sorry, it's only B. And I will modify here. Yeah, it is B. Okay, and let's talk about the other one. A standing wave on a string vibrates as shown. Here is the original one. Like suppose the string tension is reduced to 1/5. Its original value like reduced to quarter its original value, while the frequency and the length are kept unchanged. Which standing wave pattern is produced? Like which means the string tense, like we know like the F, the frequency and the length is the same thing, but the string tension is reduced to half. Yeah, which means like F, we know F equal Fm equal mv divided to L, am right? And the frequency is the same thing, unchanged, and the length unchanged. So which means and the string tension like equal m like 1 to L divided tension divide, yeah, which means tension will be like 2 4, which means here is uh, it's same thing. And well, which means it m should like it should 2m, and then it will keep the frequency same. Am I right? So the mode number should be increased like like multiple two times. Does it make sense to you? Okay, let me try to write it clearly to let you to understand. Yeah, here equal what? Like 1 divided to like 10 tension, and mu, like here this is m divided 12. This one will keep the same because the like length and frequency will keep the same, like the mass is keeps the same, and L will keep the same. And here the 10 tension is reduced to 4 over 1 over 4, which means the new tension is uh, like this this like for example, we want to new mode. We will now write it, and then e, yeah, it will become 1 over 40 and a mu, and this one will equal to what? To L1. And you can see we want the frequency same, am I right? So we need multiple 2m. Then here is it's the same thing. The frequency will keep the same. So which means we should let the m twice before. Here, the original is 2. It should be 4 after twice. Does it make sense to you? So the right answer should be C. Does it make sense to you? Yeah. Yeah, it is C because we use this equation. Yeah, countering the tension reduce V by 1/2. Thus, M must double to keep the frequency constant. Does it make sense to you? Okay, let's like talk about the other example, like setting the tension in a guitar string. The fifth string on a guitar plays the musical note A at a frequency of 110 Hz. On a typical guitar, this string is stretched between two fixed points, uh, 0.640 meter apart. And this length of string has a mass of 2.86 gram. What is the tension in the string? Okay, we also refer to the equation 16.5, like F equal V R 2L. And let strings sound at that fundamental frequency. So like yeah, we know that strings sound at their fundamental frequency. So 110 Hertz is the fundamental frequency. Here is a fundamental frequency. Yeah, there are some like a musical like a background. Yeah, like plays the musical note A, which means their fundamental frequency here. And then let's try to resolve the linear density of string is equal like m divided L. M, we know that here 2, and L, we also know that, sorry. Uh, yeah, okay. The L, we know that here is like the string is joined between two fixed points. Yeah, this is the L, and then we know the linear density. Yeah, and of the string, and we can rearrange this equation. Yeah, equal what? T mu. Does it make sense to you? We can arrange this equation and let it. Oh, sorry. Sorry to let this equation. Yeah. equal this one. Yeah, because here we know this one, and for the fundamental equation, it is 1 over 2L T mu. So which means T equal what? T tens will equal what? R to F1 and square and multiple mu. Does it make sense to you? So we can get this equation and we put 2 here, length here, fundamental forms here, and this is like a linear density. So and the finally tension of this string is equal to this one. If you ever like strummed a guitar, you know that the tension is quite large. So this result seems reasonable. If each of the guitar's 6 strings have approximately the same tension, the total force on the neck of the guitar is a bit more than 500 big. Am I right? But you can see if you play the guitar, you know the tension is big. Yeah. Okay. Let's talk about the other thing, like standing electromagnetic waves. Electromagnetic waves. Do you remember what is that? I talk about the waves, and for most of the wave can be divided into 2 waves. One is traveling waves, sorry. One is like mechanical waves. Mechanical wave means it travels through a medium. Doesn't make sense to you? The electromagnetic waves, which means it doesn't need the medium to travel, such as a light wave, such as like microwave, such radio wave. Yeah. So for the like string wave, for the sound wave, it has a standing wave. And for the electromagnetic wave, it also has a standing wave. So like let's talk about this. A laser establishes standing light waves between 2 parallel mirrors that reflect light back and forth. Yeah, you can see here is 2 mirror. And let me try to close this. I don't know. Yeah. Yeah, this is 2 mirror. And like this light waves, if this is the standing light waves, the mirrors are the boundaries, and therefore the light waves must have a node at the surface of each mirror. Yeah, we talk about this. If this is a standing wave, here must be a node. Node. Yeah, does it make sense to you? Okay, this is a full flexion. This is a partial flector. This is a full flector. This standing light wave. This laser cavity. Here is a laser beam. Okay, and yeah, this is like this standing electromagnetic waves tell us like also for the like electromagnetic waves also it can generate standing waves. Yeah, so, it has a superposition like a situation. Yeah, does it make sense to you? It's similar with the string waves, sound waves. Only like it is like electromagnetic waves. Does it make sense to you? Okay, let's talk about one example. Like finding the mode number for a laser. A helium nano laser uh, emits light wavelength lambda equal 633 nanometer. And a typical cavity for such a laser is this one. It's 50 centimeter long. What is the mode number of the standing wave in this cavity? Yeah, just like a standing wave on string, the standing light wave has nodes at each end. So equation 60.1 applies. Like m equal 2l divided divided lambda. Yeah, this equation. And the standing light wave in a laser carrier has a mode number m. Yeah, it's just like this. This is 2m because this 50 is just the length and the 2 length, and the lambda is this one, and then the m equal this one. Just pay attention. Here is nanometer, not meter. So you need to do the unit transfer, and the final mode number is 474,000. Yeah, you can see. Let's assess this question. The wavelength of light is very short. You can see the wavelength is very short. So we'd expect the nodes to be closely spaced. Yeah, which means because the nodes is half like a wavelength, so it should be very close. Yeah, so which means the M a high mode number seems reasonable. Yeah, you can see this is 50 centimeter, but the node is very short. Doesn't make sense. So which means the M should be huge. Doesn't make sense to you? Okay, let's talk about standing sound waves. Actually, we have already talked about the standing strain waves and standing electromagnetic waves. Here we talk about standing sound waves. Actually, the standing sound wave is a little different with standing strain waves and standing electromagnetic waves, and we will see how different. You can see, sound waves are longitudinal pressure waves. The air molecules oscillate. Here is the air molecules oscillate like a right and left. Yeah. For example, here is a speaker, and it will left and right to oscillate, like creating compression and rarefaction. And sound waves traveling in tube eventually reach the end where they encounter the atmospherical pressure of the surrounding environment. Here, it is like a discontinuity, much like the small loop meets the big loop. Yeah, here. We talked about this just now. If you don't remember, here. Yeah. Sorry. Just yeah, here it's just like this a small loop like meet a big loop, and then it will generate a sorry like a forward wave and the backward wave. And okay, let's continue to talk about the sounding standing sound waves. Okay, like the small loop meets the big loop. Yeah, and like a part of the wave's energy is transmitted out into the environment, like here from this end, and part of the energy is transmitted into the environment, allow you to hear the sound. Yeah, and part is reflected back into the temp. It's just like the small loop meets the big loop, and part is transmitted into the environment as others is reflected. Because the end of the tube are open to the atmosphere, the pressure at the end is fixed at atmospherical pressure and cannot vary. Here, the pressure is fixed. So this open end of column air must be a node. Here must be a node of the pressure wave. Yeah, since the pressure here is fixed. Okay, and a column of air open at both ends is an open tube. Yeah, here, if this tab, this end is open, this one tab end is open, we call it open tab. And because the end of the tab are open to the atmosphere, so the pressure at the ends is fixed at atmospherical pressure and cannot vary. Yeah, we have already talked about the antinodes of a standing sound wave are where the pressure has the largest variation, maximum compressions, and rarefactions. And you can see here here is the compressions with maximum displacement. Rarefaction it is like a negative maximum displacement. Yeah, and does it make sense to you? Yeah, and here we'll generate the antinodes, and here is the nodes. Yeah, this is for the open tab. And but here, like there is the other kind of the other two kind of tabs, and air molecular zinc tabs that are closed at one or both ends will rush towards the wall, creating a compression, and then rush away, leaving a rarefaction. Which means if here is closed, and then when the wave hit here, it just form a compression, and back here, if it is closed, it is rarefaction. Yeah, and then back rarefaction. Yeah, so like a closed end of the air column is an anti-node no pressure. Yeah, because you can see here it hits here, it will like form a compression, which means here is an anti-nodes. Yeah, like a closed tab, like which means two ends are closed, and an open tab, which means two like end are open, have wavelengths and frequencies that are the same as those of string had at both ends. Yeah, those two is just similar as a string like a string thing. Yeah. And the fundamental frequency of an open-closed tab is half that of an open-open or a closed-closed tab of the same length. Yeah, if this tab, like one end is closed and one is end, so it is a little different, and the fundamental frequency is half that of an open-open closed-closed tab. Yeah, of the same length. So yeah, we have this equation. The wavelength and the frequency of an open tab and a closed tab, we have this equation. It actually is similar like the string like a wave, and the standing string wave and standing electromagnetic wave. It's a similar thing. Yeah, lambda m equal to L divided m. Yeah, we know like lambda equal V, sorry, no, this one. Yeah. Yeah, V equal lambda F, am I right? So like lambda equal V divided F. Yeah, so like here, F equal this one. So like here we know like the frequency will half, am I right? So the frequency will from here. So which means the lambda equal this one. Doesn't make sense because the frequency is half compared with the open tab and closed tab. So which is the frequency for open closed tab, and then lambda equal, according to this equation, we can get the lambda equal 4L divided m. Does it make sense to you? Yeah, okay, this is a little different. Yeah, okay, let's summarize this like standing sound waves. Yeah, here is the first three standing sound waves modes in columns of air with different ends. Yeah, here is the open. This is open, and you can see here is nodes, and this is just M1, and here is nodes. Yeah, and close, and because here it hits the like end, and it will generate a like compression. So this will be a antinode, and then here is an antinode. Yeah, also the ends, and for open and close here. And for the closed part, it will be the antinodes, and for the open part, it will be nodes. Yeah, similar thing, it is nodes, antinode. Yeah, so this is for the like a standing sound waves summarized. Let's see like a video if here.
Standing sound waves in tubes, so I can have different boundary conditions. You can have tubes which are open at both ends, and if it's open at both ends, the pressure wave has a node at both ends. Or I can have sounds sound waves which are in tubes closed at both ends, like this auditorium works like a tube which is closed at both sides, and there's reflections from both sides, and it's got certain resonant frequencies of the room. Or I can have open-closed tubes. I can have a tube which is like closed at one end and open at the other. And then I have a node here, and then I have at the other end, the closed end, I have an antinode. And so the boundary conditions give you different possible harmonics. And you have relationships which tell what the different harmonics are. The only trick is to figure out what kind of boundary conditions do you have? What kind of tube is it? So for instance, let's look at this one. We have these big plumbing pipes that we use in Little Shop of Physics to make music. And we just took like sections of PVC pipe and painted them special colors, and that's it. That's it. And we can play music on these. So with this lowest one, we want to calculate what is the length of the lowest tube right here, okay? But this one right here, the thing we need to know is, what are the boundary conditions? Looks like it's open at both ends to me. So this is an open tube. And when I play it, I'm going to play it with a pop gun, which I insert in the end of the tube. I don't close it. Wednesday in class, you're all going to play shorter tubes. And the shorter tubes, you pound on with your hand. And if your hand's on one end, that makes that end closed. But these stay open. So this one's open. The one we do in class is open, closed. And actually, that makes a difference in terms of how you calculate the length of the tubes. Well, this one's open at both ends. And so we can work out what the length of the tube is by this. We say, oh, it's an open tube. And the frequencies are this. Fm is equal to m times v divided by 2L. Then we say, oh, how do I know which harmonic I want to use? The pitch, if I say it's 64 hertz, that means it's the fundamental. That means it's F1. F1 is 64 hertz. And so that's equal to 1 times V over 2L. The higher harmonics don't determine the pitch. The higher harmonics determine the tone quality. So you can tell this is music which is being played on PVC pipe as opposed to being played on tin pipes in an organ. Okay? So those higher harmonics tell you that. But the pitch is fixed by this. Oh, so all I need to know in this equation is the velocity. What do we use for the velocity? The speed of?
Yeah, you will like answer these questions later.
Sound in air, and that's like 340 meters per second. It's 343 meters per second at 20 degrees Celsius. It's not 20 degrees Celsius where I'm standing, so we're going a little bit lower than that, our typical average value here. And I can calculate the length, and if I do that, I get a length of 2.7 meters. In fact, that's how we calculated how long to make the tube. Now, if I make a shorter tube, what's that going to do to the pitch? Higher pitch. Oh, and I've got a whole series of tubes with different colors, going from like long, and then successively shorter as I go down the way. And so I can get different pitches out of here. And in fact, to be able to play music, you have to have the ability to have different pitches. And that's how we get it here. The different length tubes, we just cut them to different lengths. And what I'm going to do is this. I'm going to play them with this pop gun. Now, when I do the pop gun, it makes this percussive sound. And actually, it's a mix of different frequencies. It's a mix of different frequencies. But when I do the pop gun inside the tube, what happens is this. There's a whole bunch of different frequencies inside the tube. The only ones that will persist are the ones that correspond to resonance frequencies of the tube, i.e. the standing wave modes. Listen. Or. And so you can actually play music. All right. And you're using the resonance frequencies of the tube to do that. And the pop gun is just all about exciting it. You can do it with whoopee cushions, too, which is more fun at parties.
Interesting, I'm right? Yeah. So like yeah, you can watch this video later and also like do the questions. It's easy for you, I think. Yeah, let's continue to talk about this. And yeah, let's do some questions to quick check what we have already learned. Yeah, here an open tub of air has length L. Which graphic shows M equal 3 standing waves in this tub? Yeah. What does it mean? Like which means like here, because it is like open, so it should be like nodes, am I right? But here and M equals 3, so which means what? Which means there should be 3. Sorry, there should be 3 like a standing wave, am I right? So I think it's obvious, and it should be A, am I right? Yeah, because we graph show M equals 3 standing waves in this tab. Okay, let's continue to talk about like an open close. Yeah, I think here is close, here is open. Tub of air of length L has the close end on the right, which graphic shows M equals 3 standing wave in the tub in this tub. And the open close, which means the frequency will be half, am I right? So like the period should be like a uh, if and otherwise this here is end, so which means so here is closed, so which means this is antinode, am I right? So which means this one or this one, am I right? So here I'm equal 3, but you can see the frequency should be half. Yeah, we have already talked about that, am I right? So it should be here 1.5 like that. Does it make sense to you? So which means it should be C. Does it make sense to you? Yeah. Okay, let's talk about the other one. The following tab will output sound waves at their fundamental frequency. Which tab has the lowest fundamental frequency? Yeah, this one is open, open. This one is close, close, and this one is open, close. Because open, open, close, closed, it's the same thing. So it must be C. Does it make sense to you? Because it's half the frequency. Does it make sense to you? Okay. Let's talk about the other one. Which of the following changes will increase the frequency of lowest frequency standing sound wave in an open tab? Choose all that apply. Yeah, for this one, we need to like write what is the open like frequency. It is what? It is MV divided 2L. Am I right? And mm, yeah, because it is like the lowest frequency, so it is the like it is the this one should be 1. Does that make sense to you? Let me, yeah, this one should be 1, and yeah, it should be equal this one. And okay, let's talk about how to like increase this frequency. Choose one end of the tab. One end of the tab, which means like a open end. So which means it will decrease the frequency. So this one is not right. Doesn't make sense to you. And replacing the air in the tab with helium, which means like the helium, like which means what? Which means let's write this one over 2 divide sorry, like T. Maybe T here. This is for the sound. So we need to use the other equation uh, for the sound equation. Let me try to yeah, like it should be use this equation. Sorry. Mm, like R T M. Yeah, this is V, and it should be related to the temperature and mass, and replacing the air in the tub with helium, which means this one will be decrease, and this one should be increased. So this one is right, and reducing the length of the tub. So which means this one will reduce. This one it means the frequency will increase. So this one is also right. Increase in temperature of the air in the tub, which means this will increase, like the frequency will increase. So this one is also right. So like the answer should be B, C, D. Does it make sense to you? Okay, let's continue. Let's check this example question. At room temperature, the fundamental frequency of an open tap is 500 Hertz. If taken outside on a cold winter day, the fundamental frequency will be so like the fundamental frequency equal what? V 1 divided to L. Like I just read it down. Sorry, here like this equation like R So RPM, right? So it is cold. So temperature like in decrease. Am I right? So the frequency will decrease. So it should be less than 500 hertz. Yeah. So it should be A. That makes sense to you. Okay. Yeah, this is like a for the like a standing wave mode, like modes. Yeah. And here there are only two sets of frequency and wavelength relationship for standing wave modes. And here wave on string with fixed ends. Yeah. Here is for the like a string with fixed ends, and yeah and also like the sound wave in open tab and the sound wave in closed tab. Those three actually they have the same situation. They share the same equations. Yeah, lambda equal this one, frequency equal this one. Yeah, we have talked about. And for the sound wave in open closed tab is different. Yeah, because the frequency is half that one, and lambda should be twice this one. Yeah, does it make sense to you? So you need to try to understand this and know how to calculate frequency and wavelengths using according to different situation. Yeah, using this equation. Does it make sense to you? Okay. Let's try to talk about how to resolve the problem about standing sound waves. Yeah, we can use the same general approach for any standing waves. Yeah, not only the sound standing waves. Yeah, yeah, standing waves occur whenever a wave is confined between two boundaries. In this case, only certain modes with particular wavelengths and frequency can exist. Yeah, for sound waves, yeah, for sound waves, determine what sound of tabs or tab you have, open, or close, or open. Yeah, for the sound waves, firstly, you need to check if it is open, close, or open, closed. For string and net waves, the ends will be fixed points. Otherwise, it cannot generate standing waves. Yeah, just it must be fixed point. Yeah, for other types of standing waves, such as electromagnetic or water waves, the more diagram will be similar to one of the cases outlined in synthesis 16.1. Yeah, just this thing, and you can then work by analogy with waves on strings or sound waves in tabs. Yeah, you can also find the similar situation. Determine known values, length of the tab or string, frequency, wavelength, position of nodes or antinodes. It may be useful to stretch a visual overview, including a picture of the relevant mode. Yeah, sometimes yeah you can see if you draw this stretch this and wave looks like it will help you to resolve this problem. And then once you determine the mode diagram, you can use appropriate set of equations in synthesis 16.1. Yeah, just this picture. And sorry. And then find the wavelength and frequency. These equations work for any type of waves. And assess, does your final answer seem reasonable? Is there another way to check on your results? For example, the frequency times the wavelength for any node should equal the wave speed. You can check to see that it does. Okay. Yeah, this is like how to resolve, how to uh, resolve the problem like related to standing waves. Yeah. Okay. Let's talk about one example. This is a biology example, like a resonance of the air canal. Like the air drum, here is an air drum. Yeah, which transmits vibrations to the sensory organs of your air, lies at the end of the air canal. As the figure shows, the air canal in dots is about 2.5 centimeter at this one. Yeah, in length, what frequency standing waves can occur within the air canal that are with the range of human hearing? The speed of sound in the warm air of the air canal is this one. So you can see here, this is just like the sound wave pass through this tube. This is a kind of tube, and this tube is an open end tube. Does it make sense to you? So the air canal acts like a tube that supports sending sound waves. Yeah, we proceed according to the steps in problem solving. We just talked about that. We can treat the air canal as an open-closed tube, open to the atmosphere at the external end, closed by the air drum at the other end. The possible standing wave modes appear as in figure like 16.19c. You can check this in textbook. The length of the tube is 2.5 centimeter. Yeah, so then from the equation 60.7 gives a allowed frequency in an open closed tube. We are looking for the frequency in the range, this one. The fundamental frequency is this one. Yeah, we have the equation, and this is a velocity, this is the constant, this is the length of the tube. So we can have this frequency. Yeah, and the hair the hair harmonics are odd multiples of the frequency. Uh, do you know why is just like this? I think I forgot to tell you. I didn't express this here. You can see for an open close tab, and you can see it, because you can see here is no node, here node, so you can have the mode like a even like a time to form this situation. But here one is node, the other is antinode. One is node, the other is antinode. So which means here you can now like choose an like a even number like for the modes. Yeah, for the antinodes, there must should be like the odd number. There will not be the even number. Yeah, for that. Yeah, does it make sense to you? Otherwise, you cannot like one side is node, the other side is antinode. It will not it will impossible for this situation. So this should be odd number. Yeah. Okay. Let's continue. Yeah. So since it should be odd number, so it will be one. This is one. This is 3, 5. This one. So like the question asks us like uh, what frequency standing curves with with the range of human hearing, speed of sound that one. Yeah, this just like so. Those like three like is uh those three like frequency standing waves can occur within the air canal that are with the range of human hearing. Yeah, does it make sense to you? Okay, let's check the other like thing. This is what we should know. Like the curve of equal precise lawless shows and intensity level required for different frequencies to give the pressure of the equal lawless. You can see for the accuracy you can like if your sound intensity level is small, not that big, you can also be heard. But for the low frequency, you need a high sound intensity level, and then your voice can be heard. And you can see the two deep here and here on the curve are resonance in the air canal where pitches that should seem quieter produce the same perceived noise. You can see here and here it is some kind of like resonance. So even the frequency here is small, like the sound is small, and our ear also can hear it clearly because the resonance situation. Does that make sense to you? Okay, like here are some like wind instruments, like the wind instruments like a flute thing. Use holes to change the effective length of the tube. The first open hole becomes a node because the tube is open to atmosphere at that point. It is open. The instruments with buzzers at the end or that use vibrations of musicians' lips generate a continuous range of frequencies. The ones that match the resonances produce the musical notes. Yeah, this is how these wind instruments do. Yeah, let's see an example like the importance of warming up. Wind instruments have an adjustable joint to change the tube length. Players know that they may need to adjust this joint to stay in tune. That is to stay at the correct frequency. To see why, suppose a cold flute plays the note A at 440 Hz when the air temperature is 20 degree. How long is the tap at 20 degree? The speed of sound in air is this one. This is question A. Question B. As the player blows air through the flute, the air inside the instrument warms up. Once the air temperature inside the flute has risen to 32 degrees, increasing the speed of sound to 250 meters per second. What is the frequency? At the higher temperature, how must the length of the tube be changed to bring the frequency back to 440 Hz? Actually, yeah, those we just use like these equations here listed in synthesis 60.1 to resolve these questions. Yeah, and yeah, a flute is an open tube with frequency fundamental frequency f1 equal v divided 2l. We know the speed of sound v and the frequency f1, so we can find the tube length. And a higher speed of sound will then lead to a higher frequency. Finally, using the higher speed of sound, we can find the new length of tube that will give the required 440 Hz frequency. Yeah. And a flute is an open tube with fundamental frequency. This one, we should use this equation. At 20 degrees, the length corresponding to 440 Hertz is, yeah, you can see you have this equation, and then L equal what? L equal V2, this one. Yeah, that makes sense to you. And then you can get the flute is 0.390 meter. And as the speed of sound increases, the frequency changes too. Yeah, you can see the speed changes, and the length is the same thing. So you can get the new frequency, 449 Hertz. And to bring the flute back to tone, the length must be increased to give a frequency this one with the speed of this one. The new length is, yeah, you can see like a, yeah, the frequency should be kept this one, and this is the velocity, and we can get the new length. Three. Yeah, you can see this one and this one is quite similar. Yeah, the flow must be increased in length by 8 millimeter. A small change in the absolute temperature produce a correspondingly small change in the speed of the sound. We expect that this will require a small change in length. So our answer makes sense. Does it make sense to you? Yeah. So yeah, we just if you met these problems and you just try to analyze it and find the suitable equation from this, yeah, synthesis 60.1. Yeah, does it make sense to you? Okay, this is what we learn, yeah, today. And we learn the superposition and the standing wave. For the standing wave, we learn different like a standing wave, like the string standing wave, like electromagnetic wave, and also like some standing sound wave. For standing sound wave, according to different types, and you can and there are different equations to find the frequency, wavelengths, and the length, like tab length, like that. Yeah, so this is what we learned today. So hope, yeah, we will also have a lab today. So hope you can finish everything in time. And if you have some questions, problems, you can find me in my office hour. Also, you can, if you don't have time in the office hour, you can schedule with me. Like we can have a Zoom meeting, like a if like for another time. That's totally fine. Okay. Thank you. Bye.